Picture the scenario for a second. You are working in tech support or engineering.
Right.
It's a standard Tuesday. Queue levels are normal. You're, sipping your coffee, and then suddenly, bam!
Oh, yeah. The executive escalation.
Exactly. It just lands on your desk. A major customer is furious. They're threatening to churn, and they have CC'd your CEO.
The worst feeling.
It feels like a lightning strike, right? Just this completely random, destructive event that came out of nowhere.
Yeah, and now you are in full firefighting mode.
You drop everything, you scramble, you apologize.
It's that classic reactive posture. I mean, in that moment, the escalation just feels like a natural disaster.
Oh.
Unpredictable and inevitable.
Right, but today we are actually challenging that exact premise.
We are.
We're doing a deep dive into a stack of technical documentation, some engineering blog posts, and white papers from Support Logic.
And they argue these aren't random lightning strikes at all.
Not at all. They are predictable weather patterns. And if you build the right sensor network, you can forecast them before the storm actually hits.
Moving from reactive firefighting to preventative forecasting.
Yes. But to be clear, for everyone listening, we aren't just talking about some high-level marketing concept today. This isn't a sales pitch.
No, we're doing a full technical teardown.
The actual architecture required to build this. We're going to look at the escalation prediction engine itself.
We'll cover the structural flaws in your current CRM data.
The specific NLP signals that matter. And honestly, my favorite part, the totally counterintuitive math behind why a perfect model might actually look like it's failing on your dashboard.
Plus, we'll get into the weeds of the infrastructure, specifically the challenges of running this on Google's Vertex AI and the Terraform headaches the engineers had to solve to get it into production.
So let's just start right at the foundation, the data architecture. Because, when I first looked at this topic, my immediate thought was, why do we need a complex, separate AI model?
Right. Why not just use what you have?
Exactly. Can't we just query Salesforce or Zendesk, just run a select star where status equals escalated and look for trends?
I mean, you can certainly try, but you are going to run headfirst into what the engineers call the snapshot problem.
The snapshot problem. Break that down.
So think about how a standard CRM database is designed. It is effectively a state machine. It only really cares about the now.
Okay.
Is the ticket open or closed? Is the escalated checkbox true or false?
Sure. So if I escalate a ticket, the box gets checked.
Right. And when you resolve the issue and de-escalate it,
I uncheck the box.
and that right there is where you destroy your training data.
Wow. By unchecking it.
By unchecking the box to reflect the current reality, you erase the historical reality.
So if I run that SQL query next month?
That customer doesn't show up. The system has amnesia.
I see. So for a machine learning model that actually needs to learn sequences of events leading to a crash, a CRM is basically useless because it just keeps overwriting the past.
Precisely. They call this the overwrite culture. Agents update notes in a single text blob. You lose the timeline entirely.
You don't know when the sentiment shifted, only how it ended.
Exactly.
So step one in building this engine isn't going out and buying a GPU.
No.
It's fixing the database schema. The documentation suggests moving to custom objects. How does that work?
Instead of a flag on a ticket, you create a dedicated entity, an escalation object.
A separate table in the database.
Yes. It has an open date, a closed date, and a permanent record of what happened.
So it's immutable history.
Yes. And critically, it allows for many-to-one cardinality.
Meaning?
Meaning a single support case can have 3 distinct escalation objects attached to it over time.
Oh, which captures the re-escalation pattern.
Exactly. The customer who gets angry, calms down, and then explodes again a week later on the exact same ticket.
So now you have a clean time series data set. You've turned your data from a static snapshot into a movie.
And only now can you actually train a model.
Okay, so we have the clean history.
Yeah.
Now we need the inputs. The model needs to read the incoming stream and flag risks.
Right.
The sources describe this as a dual signal engine, structured and unstructured.
The structured stuff is standard fare, but it provides a necessary baseline. Things like account density.
Like, are 10 people from the same company filing tickets at the exact same time?
Right. Or case age. Or the reopen rate.
Yeah, if a ticket is closed and reopened 3 times, that is a massive structural signal of failure.
It is. But the documentation implies that structured data is just the skeleton. The meat is in the unstructured data, the text itself.
And this is where it gets super interesting, because it is not just keyword matching. It isn't just Control-F for the word angry.
Keyword matching is way too noisy. Think about it. If a customer writes, "I am not angry yet," but I might be soon.
A keyword search just sees angry and flags it.
Exactly. That's a false positive. So the model here looks for sentiment trajectory.
Trajectory implies direction.
Right. It measures the delta. It's asking, is the tone colder today than it was yesterday? It calculates the rate of decay in the relationship.
But the most specific signal, and that the white paper actually calls the secret sauce, is intent detection.
This is a crucial distinction. How is intent different from sentiment in this specific context?
Well, sentiment is I am frustrated. Intent is I am taking action. The model looks for linguistic markers of process change. Phrases like, I'm looping in my VP, or I need to speak to a manager, or this has been open for 3 weeks.
I'm looping in my VP is a terrifying phrase in tech support.
It really is, and it's a high-fidelity signal. It means the customer is done trying to solve the problem with you.
And is now trying to solve the problem around you.
Exactly. That is what the model hunts for.
Okay, so we are ingesting this data, analyzing the trajectory, and spotting intent.
Right.
Now we have to score it. And this brings us to the math.
Oh man, the math. The sources had a section on evaluation metrics that was surprisingly dense.
Very dense.
It argues that for this specific use case prevention standard, accuracy is a garbage metric.
It's the class imbalance trap. Let's just do the math real quick. What percentage of support tickets actually escalate in a normal company? Maybe 5%.
If you are lucky, yeah. Let's say 5%.
So if I write a really dumb script that just says no escalation for every single ticket, regardless of what the customer says,
Right.
how accurate am I?
You would be right 95% of the time.
Exactly. 95% accuracy. And the model is totally useless.
It predicts nothing, so accuracy is completely out.
So usually, data scientists will then pivot to precision. Of the ones I flagged, how many really escalated?
But the documentation says precision is even more dangerous here.
Yes. In fact, it argues that in a perfect system, your precision might theoretically drop to 0.
This is the prevention paradox, and honestly, this is the hardest thing to explain to business stakeholders.
Walk us through it. Why does success look like failure?
Okay. Imagine the model predicts a ticket is going to explode. It flags it. That is a positive prediction.
The alarm goes off.
Because the alarm went off, a senior support engineer jumps in. They call the customer, they apologize, they fix the bug immediately.
Right.
The customer is happy, they do not escalate.
Crisis averted.
In the real world, that is a huge win.
A massive win.
But look at the data record. The model said yes, escalation. The outcome was no escalation.
Wow. Mathematically, that is a false positive.
The model looks wrong because it was useful.
That is just wild.
Yeah.
By acting on the prediction, you destroy the evidence that the prediction was ever correct.
Exactly. If your intervention is 100% effective, your precision is 0%. You have created a completely self-defeating metric.
So if you can't use accuracy, and precision is basically a lie in this context, what do you use?
Recall, you have to look at history.
Okay.
You ask, of the cases that did blow up, how many did we catch?
Right.
You accept that you are going to have false alarms, low precision, in exchange for never missing a real fire.
That's high recall.
You optimize for coverage, not perfection.
That is a huge mindset shift for anyone building these tools.
Right.
You have to be able to tell your boss, hey, a lot of these alerts will seem like nothing, but that is the cost of insurance.
Yes.
It's like a smoke detector. You don't want a smoke detector that only beeps when the house is already burning down just so it can boast high precision.
Right. You want it to beep at burnt toast so you catch the kitchen fire early.
Exactly. So let's shift gears to the how.
Yeah, let's get into the stack.
We've got the theory, but the sources actually dive into the real engineering stack, specifically machine learning as a service, or mGlossus.
They built this on Google's Vertex AI.
Vertex is powerful because it handles the whole life cycle: training, deploying, monitoring.
But the engineers who wrote these docs ran into some very specific bleeding edge problems when they tried to automate it.
You are talking about the Terraform integration.
Infrastructure as code.
Right. You want to define your whole stack in Terraform files so it is repeatable. You do not want engineers clicking around in the Google Cloud Console manually.
Never a good idea.
But the Terraform providers for Vertex AI were incomplete at the time.
Missing modules.
Missing basically everything.
Yeah.
The engineers couldn't just write resource vertex underscore endpoint. It literally didn't exist yet in the provider.
So what did they do?
They had to use provisioners.
Oh, man. Which is basically the break glass in case of emergency tool in Terraform.
It is absolute duct tape. They had to write Python scripts that manually call the Google Cloud SDK to spin up the models.
Right.
Then inside the Terraform code, they use a local exec provisioner to trigger those Python scripts.
So Terraform isn't actually managing the resource directly.
No.
It is just triggering a script that manages the resource.
Correct. And that makes state management incredibly messy. If the script fails, Terraform might not know the exact state of the cloud resources.
It's a great example of theoretical best practice versus just getting it shipped.
Yeah.
There was another constraint with Vertex that caught my eye, the inability to scale to zero.
Yeah, that's a big one. If you use Google Cloud Run or AWS Lambda and nobody calls your API, you pay nothing. The server just turns off. Vertex endpoints aren't like that. You always have at least one node running.
Which sounds inefficient. Why pay for a server at 3 a.m. if no one is escalating tickets?
Well, the counter-argument is the workload type. This isn't a chatbot where you sit around waiting for a user to type something.
Right, it's a background surveillance system.
It runs on a cadence, scanning every open ticket every single hour.
So there really is no idle time. It is always chewing on data.
Exactly. Since the system behaves like a continuous monitoring service, the always-on cost is justified. You need that baseline compute to constantly reevaluate the risk scores.
Okay, so we have built the model. We have hacked Terraform to deploy it, and it is running.
Yep.
But the last section of the source material is about the silent killer of AI models, drift.
Model rot.
Right? The world changes. A new product launches, customers learn new words, the vibe shifts. The model you trained in January is dumb by July.
It's inevitable.
How do they actually catch that?
Well, it isn't by vibes, it is by math. They monitored two distinct types of drift, prediction drift and data drift.
And they use some pretty heavy statistical distance metrics for this.
Very heavy.
I saw Jensen-Shannon divergence mentioned.
Yes, for numerical data. Imagine two curves on a graph, your original training data and your live production data.
Okay.
Jensen-Shannon measures the gap between those two curves. If the gap gets too wide, it trips an alarm.
And what about for categories? Like if suddenly everyone stops tagging tickets as bugs and starts tagging them as feature requests?
For categorical data, they use L infinity distance.
Your infinity distance.
It measures the maximum shift in probability for any single category.
So if feature request jumps from 5% to 50%.
L infinity spikes.
And what happens when the alarm goes off?
Retraining.
Yeah.
You grab the recent data, you feed it back into the training pipeline, and you publish a new version of the model.
It's just a continuous loop.
It has to be. If you don't have drift detection, you don't really have a product. You just have a legacy system that is slowly getting dumber every single day.
That is a really sobering thought. It's not set it and forget it. It's set it and babysit it.
It is the absolute reality of MLOps right now.
So pulling this all together, we have gone from the database schema fixing that snapshot error
Right.
to the NLP intent detection, to the recall over precision math, all the way down to the Vertex infrastructure and drift monitoring.
It really is a full stack approach. You can't just buy the AI. You have to build the entire ecosystem around it.
I want to leave you, the listener, with one final thought that ties back to that prevention paradox we discussed earlier.
Rough for it.
We talked about how successful prevention looks like a false positive in the data. Think about the human incentive there.
Oh, this is fascinating.
If you are a support director and you pay your people or your vendors based on accuracy or precision,
You are actively punishing them for preventing fire.
you are incentivizing them to let the fire burn just long enough to prove the model was right.
It's terrifying.
Exactly. So as we build these preventative systems, we have to redesign our compensation plans and our KPIs to reward the absence of noise.
Value what didn't break. That is the fundamental shift.
A shift from firefighting to forecasting. Thanks for diving into the tech with us.
Always a pleasure to get into the details.
And thank you for listening. Keep thinking about those incentive structures, and we will see you on the next deep dive.